I'm Russ from Weights and Biases, and today I'll be providing a demonstration of our platform for AI model development, W&B Models. If you're already familiar with Weights and Biases, it's probably from adding our library and a couple lines of code to your Python scripts to track your machine learning experiments. But today, I'd like to paint a much more expansive picture of the role Weights and Biases can play as the AI system of record for you, your ML team, and your entire organization. To do this, I'm going to walk you through an LLM fine-tuning workflow. Before we dive in, let me quickly introduce you to some of the Weights and Biases features that we'll be using today. Starting on our right are the W&B core components, critical to successful machine learning experiment tracking. Artifacts to track and version objects such as models and datasets as the inputs and outputs of your W&B experiments. Tables, which allow you to store data, including text, images, and other data types, and display them in a visually effective manner when reviewing experiment results. Reports, to support collaboration and share crucial information, such as model evaluation results, among your decision makers. And the SDK, which allows you to log ML experiments and artifacts at foundation model scale with speed. You'll have an opportunity to see each of these features in action as we proceed through our guided tour, which will include experiment tracking, hyperparameter optimization using sweeps, and then publishing your candidate models to W&B Registry. We'll then move on to how to use automations to push these models into your CI/CD pipeline. Launch, which allows ML platform engineers to configure complex infrastructure like Kubernetes clusters and make them much more accessible to the ML engineer for training, fine-tuning, and evaluation. And finally, as part of the CI/CD workflow, candidate model evaluation, reviewing model comparison results as a team, and, pending model approval, deployment into production. If it sounds like Weights and Biases adds value to every part of the MLOps lifecycle, you're right, and we've got a lot to talk about, so let's get started. A lot of machine learning software demos start out talking about experiments, training, and fine-tuning, and we're going to get there in a minute. But if you're familiar with the ML lifecycle, you know that it's exactly that, a cycle, not a straight line. Today we're going to start our demo at Registry, the foundation for an effective CI/CD pipeline. In traditional software development, CI/CD, or continuous integration and continuous delivery, automates many tasks, including building, testing, and deploying software. CI/CD for machine learning is, of course, slightly different. The CI/CD pipeline that is a focus of this demo automates the end-to-end workflow of building, testing, and deploying machine learning models. All right, let's talk Registry. Registry is a curated central repository that stores and provides versioning, aliases, lineage tracking, and governance of models and datasets. It allows individuals and teams to share and collaboratively manage the lifecycle of all models, datasets, and other artifacts. And it's the single source of truth for production models and datasets. Everything that you need to reproduce a model, as well as explain its origins, is here. Registry provides multiple critical benefits to your MLOps workflow, including ML lifecycle management, the metadata and lineage information required to reproduce any ML task or artifact, discoverability to make all of your artifacts searchable and promote collaboration among your ML teams, and last, but by no means least, governance and access control to ensure that only the right users have only the appropriate level of access to your most valuable models and other artifacts. Registry is one of the key intersections where the paths of ML engineers and ML platform engineers cross, making it particularly important in ensuring the successful handoff, evaluation, and deployment of the new models that the ML engineer has spent so much time training or fine-tuning. This is W&B Registry. Up top, we have our default model and dataset registries. The artifacts stored in these registries are available to the entire organization, though different permission-based roles, including admin, member, or read-only viewer, can be assigned on an individual basis. Here's our dataset registry, where we store datasets that we want to share not just with our teammates, but other users throughout the organization who may find them useful for their own projects and experiments. This Alpaca Clean dataset is what we'll be using for our fine-tuning experiment today. And below the model and dataset registries, we have our custom registries. We acknowledge that different organizations are organized differently. Registry lets the ML platform engineer decide how to structure underlying registries and collections. W&B offers the ability to create multiple custom registries that can store any artifact type. And again, governance and security are top of mind. These artifacts can be shared with everyone in the entire organization or restricted only to specifically invited users from any team throughout the organization. Here's the registry we'll be focusing on today, Llama Models. And here's our collection of Llama 3.1 models fine-tuned on the Alpaca Clean dataset. Registry is primarily the domain of the ML platform engineer, establishing the CI/CD pipeline, tracking and managing registered ML artifacts, pushing models and datasets into evaluation and optimization workflows before reviewing results, and finally, settling on deployment decisions. But the ML engineer has work to do here as well. Setting up meaningful evaluations and comparisons with existing models requires setting up experiments and generating reports. The ML engineer's job in our story actually starts at the initial AI experiment. In this case, fine-tuning a Llama 3.1 model. Fine-tuning large language models using instruction-based datasets can offer several benefits, including adapting an LLM to perform specific tasks, or enhancing the performance of an LLM by providing instructions for how to more accurately perform specific tasks. There are many high-quality instruction datasets in a variety of different formats. Some are created manually, while others are made using LLMs like the Alpaca dataset we'll be using today. The Alpaca dataset is a synthetic dataset developed by Stanford researchers using OpenAI models to generate instruction output pairs. The dataset covers a diverse list of user-oriented instructions, including email writing, social media, and productivity tools. Alright, let's get under the hood now and take a look at the code for the experiments we'll be tracking. Here we have our first run. A run is the execution of a single experiment within a project. Some examples of when to initiate a new run include training or fine-tuning a model, changing hyperparameters within your experiment, or logging data or a model as an ML artifact. This first block is a very simple example of those couple lines of code I mentioned earlier that are required to tie your experiment to W&B models. Import, init, log, finish, easy. We'll get to the star of our show, the LLM fine-tuning job, in just a moment. First, I want to mention what I'm sure you already know. There are multiple libraries out there that do a ton of the heavy lifting code-wise when it comes to fine-tuning LLMs. A number of the most popular names in machine learning have W&B integrations, and as you can see, they are all pretty easy to implement. Of course, these are just quick code snippets here. But all of the W&B API options for seamless integration with ML frameworks, libraries, and tools are well documented in our publicly available product docs. The Hugging Face Transformers library, which has a great integration with W&B models, is what we'll be using today. Here's our second code block, a simplified example of the fine-tuning runs from our experiment that we'll dive into momentarily. You can see here that we've entered the project name and entity, so our script knows where to send our results. We specify the base model, configuration parameters, and here's where we pull in our dataset. Yep, it's the one I showed you earlier, stored in our dataset registry. And here's the call to the supervised fine-tuning trainer. Notice the report to setting and value here. That's the heart of our Hugging Face fine-tuning integration, which allows weights and biases to automatically capture the execution context, log model training, fine-tuning, and metrics, and version-generated model checkpoints and artifacts. We simply set this value to 1 dB, kick off the run, and watch the fine-tuning metrics and our fine-tuned model checkpoints show up in our W&B project. Here's our project page, Experiment Tracking Headquarters. This little green dot shows us that the job we just kicked off in our collab is still running. And you can see the long list of fine-tuning jobs we've already run previous to this one in our effort to create the best performing model to eventually deploy into production. And here we have all the results from our previous runs. Charts visualizing our training and evaluation metrics, including column charts, line charts, scatter plots, and parallel coordinate plots to identify which hyperparameter combinations are generating better models. And tables containing answers generated from prompts in our evaluation dataset. The tables are invaluable as a way to permit a human-in-the-loop review of intermediate predictions across our experiments. We can also see data from the system where these jobs were run, such as GPU utilization or memory allocated. We can drill down into any specific experiment to see just the data, charts, and metrics associated with that run specifically. Here we can get an overview of this run. We can see the start time, the duration, the system hardware, config parameters, logs from the run, the files present in the file system where we executed our code, the actual code from the run, and all of the input and output artifacts associated with this job. This is where we can see the dataset that was used for fine-tuning, as well as all of the model checkpoints that were generated. Let's take a look at our final model for this run. Clicking on the model, we can see the aliases and other information about this version. The metadata associated with the model, such as config settings and training and evaluation metrics. Remember that report 2 equals 1 dB setting in our Hugging Face supervised fine-tuning trainer call? Pretty great payoff for such a simple integration. We can also see the syntax for how to use the model and what other jobs have done so. The files associated with the model, and the lineage of this artifact. A comprehensive, directed, acyclic graph that tracks everything from the input dataset to artifacts produced by our run, and even other runs that have used these artifacts. The lineage graphs and supporting data available in weights and biases provide the exact recipe for any given artifact, allowing you to reproduce any model, address audit inquiries, and adhere to industry and company policies. A couple more quick things I'd like to show you. First, our hyperparameter optimization feature sweeps, which I mentioned earlier. You can see here a number of sweeps that I've run as part of this project, and if I click on one, you can see all of the runs associated with a particular sweeps job. This chart up top tracks how different hyperparameter values affected key metrics of interest in our fine-tuning experiments. We saw this type of parallel coordinates chart earlier when examining the combined results from all of our experiments in the project. This chart is automatically generated for each sweeps run to track which hyperparameter values are associated with the best results. And before we leave the project area, I'd like to show you the Jobs tab. I showed you code from one of our runs earlier. Jobs is a way to take that code and reproduce those earlier runs on different compute configurations set up by our ML platform engineer. It's important to note that weights and biases is compute and infrastructure agnostic, so tracked experiments in this project could be run on virtually any compute configuration, and the results can still all be collected and reviewed here in your workspace. A little more on that in a bit when we discuss model evaluation as part of our CI/CD workflow. Now that we've explored the project page and some experiment results, let me show you how we publish a model to registry, handing it off to our ML platform engineer and our CI/CD workflow for further evaluation, including comparing it to our current production model version. First things first, let's select the model that we feel is the best candidate for production deployment. Given the nature of our fine-tuning use case, we've been paying particularly close attention to a couple of metrics used to evaluate text generation and summarization: the Rouge 2 score and the Blue score. If we want to quickly filter on only experiments that achieved a higher Rouge 2 score, we can use filtering directly in the parallel charts plot. Simply click and drag on the top section of this chart to show the results from only these experiments. Whereas our current model deployed in production as the highest Rouge 2 score, we've recently made the decision to favor the Blue score in our candidate model selection, but we still want a model with a relatively high Rouge 2 score. Looking at this scatter plot that shows blue score on the y-axis and Rouge 2 scores on the x-axis, we can see the run that generated our current production model out here, Swept Snow 159. And as our new candidate, we're going to select this model generated by a more recent run, Def Thunder 310. The model generated by this run has a high Rouge 2 score and the very highest blue score of all of our runs. There are a number of ways to search and filter results from within our workspace. We also could have taken a look at this view of all of our runs and sorted on a specific column, in this case, eval blue. All right, now let's go ahead and add our model from Def Thunder 310 to registry. I just click on Def Thunder 310, then click on Artifacts, and we can see all of the models created during this run. I'm going to choose the last version of this model, version 5. And then I'm going to click Link to Registry. I select a registry, which is our Llama Models Registry that we took a quick look at earlier, and a collection, Llama 318B, and then I'll click Next Step. I have the option to add an alias right now, which I might do under normal circumstances, but I'm going to hold off for a moment to better demonstrate how aliases can be used to trigger event-based actions, in this case, kicking off our CI/CD evaluation workflow. So I'll just click Link to Registry, and we'll follow our model over to the Llama Models Registry. Here's our list of all model versions in our Llama 318B collection. Version 0 is our model version currently in production, and as such, it features the production alias. And here up above it, you can see the model that we just linked. As our latest published model, it receives the latest alias and a new version alias automatically. And when I click on the model version, we can see all of the same information and tabs that we saw when we examined an artifact earlier inside of our fine-tuning project. The run that generated the model, when the model was created, all of the metadata for the model, how to use the model in future experiments, and what other experiments have already used this model, the files associated with the model, and of course, the detailed lineage graph. Now let's take a look at the artifact card for this model and the automations that we've created to push this model into our CI/CD pipeline for further evaluation, review, and deployment. So, here we've got our artifact card, complete with searchable tags, the full name of the model, and the date it was originally created. We can also see any automations associated with this collection and set up Slack notifications to proactively alert interested parties whenever a new artifact version is linked to this collection. Below that, we can see all of our model versions and some of their respective key performance metrics. And at the bottom, the automations that we've created to automate moving these models into our CI/CD pipeline when a specific action occurs. Automations are event-based triggers set up by the ML platform engineer, making the model promotion process more efficient by eliminating what might otherwise require a manual step to move the model into the next phase of the lifecycle, such as testing or evaluation. Let's take a quick look at our two automations. We'll start with model evaluation. We've got a name, a description, trigger the webhook, review code GitHub actions whenever the alias candidate is added to any version in the collection Llama 318B. An action type, webhooks, and down below, we have a payload, where the ML platform engineer can specify any additional data that should be added to the webhook request. This automation sends a value of evaluate model as the event type, which will be used to trigger a specific workflow action in GitHub Actions. You can also see a number of other key value pairs included in the payload, provided by weights and biases to provide additional information to whatever service receives this request. The model deployment automation is much the same, only the event type is deploy model, as it is used to kick off a GitHub action to send our fine-tuned LLM to an inference server for production deployment. Let me show you how easy it is to add an automation to a collection. I just click the Create Automation button, select a team, an event type, either adding a new model version or a new alias to a model version, and an action type, which can be either a webhook or a launch job. You'll recall that I briefly showed a couple of these jobs earlier in our fine-tuning project. These are experiments created from existing code that can be reproduced and executed on a variety of different compute configurations set up by our ML platform engineer. We can either kick off one of these existing jobs as part of our automation, or we can specify a webhook. I'm going to select New Version is added to a collection and Webhook, and then hit the Next Step button. I have a number of webhooks set up, essentially destination URLs for the payload we want to send. Then I just specify a payload, name the automation, and we're all set. Before we go any further, let's add the candidate alias to our latest model and kick off our automated model evaluation process. To do this, I simply click on the model version and then add the alias, candidate. We'll check on the progress of our evaluation process in a moment. But first, let me show you the launch compute configurations that I mentioned a moment ago. Here we can see references to all of the different environments made available by our ML platform engineer. The one we'll be using for our model evaluation automation is here, ReviewCo Lambda A10. If I click on it, I can see all of the jobs that have run here previously, and also instructions for how to add an agent which will run on this cluster, polling for queued jobs to pick up and execute. Now, without further ado, let's check out our GitHub action responsible for running our model evaluation process. Our GitHub Actions workflow is proceeding step by step through our evaluation, which is essentially a comparison between our candidate model and our current production model using a number of LLM testing datasets measuring performance and accuracy. This comparison is executed as separate launch jobs, and when they are complete, a W&B report is automatically generated, delivering the results. In addition to the automated evaluation and report generation, our GitHub Actions workflow also sets up an inference server for deployment of our candidate model, so that we can do additional prompt testing using W&B weave traces. This run of our evaluation process won't be done for a little while, so let's take a look at one of the reports from an earlier evaluation. Here's the evaluation report that we can make easily accessible to all the decision makers on our team. And if we want to make the report available to anyone beyond our immediate team, we simply click the Share button and invite any other individuals with whom we'd like to share the report. Looking at the report, below the overview, we find what we're looking for, the evaluation results. We've got a toggle here that allows us to view all of the evaluation result data or only the differences between the two result sets. And below, we can see 3 column charts, one for each of the datasets that we use for testing: HelloSwag, Lambda OpenAI, and Winogram. We can see that while our candidate model did not perform as well on the HelloSwag comparison, it beat the production model in the other 2 tests. For the sake of our demo, we'll consider this good enough to move our new candidate model into production, and we reached a fitting end to our demonstration. After exploring experiments, touching on sweeps, learning about registry, automations, and launch, we conclude by deploying the model generated by Def Thunder 310 into production via our CI/CD pipeline. I just click on the model version, remove the candidate alias, add the production alias, and let our model deployment automation do the work. And that's a wrap on our demonstration of W&B Models, the system of record to train, fine-tune, and manage AI models. Thank you so much for your attention, and I'd like to extend an invitation to those of you not already using weights and biases to get started today. Just head on over to wanddb.ai and click the sign up button up top.